Okay, so chapter 3 is on graphing quadratic equations. So I've split this first section up into two parts, and we're just going to focus, kind of divide our focus in what we're doing here. So 3.1a is investigating quadratic functions in the vertex form y is equal to a x plus or minus p squared plus or minus q. Now what you're going to find as you're working through this and eventually get into pre-calc 30 is they change their variables that they use. They mean the same thing or they do the same thing. But in pre-calc 20 they use PQ, and when you get to pre-calc 30 they use HK. So if you see any that the variables still act the same way. They do the same transformations to our graph. So first of all, we're just going to start with regular table of values and find out how this graph would look. So our base graph is y is equal to x squared, and we're going to use the table of values to solve that. So what we would do then is we're going to substitute whatever our x is in the table into that equation and solve for y. So for our first one, we'd have y is equal to negative 3 squared. So that's just 9. So you have to remember when you're doing these, whatever the x value is, the whole thing is squared. So because that had a negative inside the bracket, we squared the bracket. So negative 2 then would be 4. Negative 1 is 1, 0, 0, 1 is 1, 2 is 4, 3 is 9. Okay, so we're going to graph our points here. 0, 0 is right here, our beginning point. So our first point was at negative 3 and 9. Second point was at negative 2 and 4. Oh, I'm missing a line in between there, so let's put our dot there. Sometimes when I copy them from Word into Smart, it deletes random lines. Negative 1 and 1. 0 and 0, and then we went to 1, 1, 2, 4, and 3 and positive 9. So if I connect my dots there, what I have is kind of a U-looking graph. So this shape of this graph we call a parabola. And it occurs when the equation has an x squared term, and the 2 would be the highest power. If this had an x cubed in it as well, it would no longer be a quadratic equation. In the box on the right there, it says a quick way to graph. When you've got a basic graph of y is equal to x squared and you don't have any type of transformations that you're working with on it, you can just do a basic count from there. You're going to graph your vertex, so I'll do this one in red. So I'm going to start at the vertex and I'm going to graph 0, 0. So this would be 0, 0. And then I go over 1, up 1. Then I go, and I do that both on the left and the right side of it. So then I go over 1, up 1. Then I go back to my vertex, I go over 2, and I go up 2 squared, or 4. So over 2, 1, 2, up 4, over 2, up 2, puts me at 4. So you always go back to the vertex. If I go over 3, then I'm going to go up 3 squared, which is 9. So over 1, 2, 3, up 9, puts me here. Over 3 to the left, so it's negative 3, up 9, puts me there. So you can see by doing my up and overs, or over and ups, I end up with the exact same graph. And you'll see as we move in this chapter, using that basic count is going to save you a lot of time instead of doing a table of values. The only thing is you have to remember whatever you move over, you have to square when you do the up movement for it. Okay, so just a few characteristics. Parabolas have a vertex, which is a middle point. So for y is equal to x squared, the graph that we have, it is at the point 0, 0. And we show that it's a vertex and not just a coordinate by putting that V in front of there. So the vertex is the point where your graph is going one direction and it stops and goes back up another direction. Parabolas have an axis of symmetry, which is a reflection line that splits the parabola into two symmetrical branches. Or two sides that are mirror images of each other. It can be shown with the dashed line. In this example, the equation of the axis of symmetry is, so if we look at this one, the line that is going to cut this graph so that it is perfectly in half, our two branches are identical, would be going right through that x is equal to 0. So I'll do mine in a purple dashed line. And again, I would do my arrows to show that this could continue. We just did it for those many points. So the axis of symmetry is always given as an equation, and for the ones, any graphs that we're looking at, it's always going to be x is equal to, and then whatever that dotted line goes through. So in this case, it's 0. Parabolas can open upward or downward. If they open upwards, they go up forever and ever, but only go down so far. Therefore, they have a minimum value. So this graph that we have up here, we could only go as far as 0, and then that was the minimum value we could have. Then the graph turned around the other direction and went up. In the example above, the minimum value is y is equal to 0. So my x's, if I look, I can continue to expand going across this direction and this direction, but my y ended right at that y is equal to 0 spot. If they open downwards, they go down forever, but only go up so far. So if this graph was flipped so it looked like this, then this point here would have a maximum value. That y would be at a maximum and everything else would go down. For any graph, you can find the domain. I don't know why I left that blank. How far left does the graph go and how far right does the graph go? That's what the domain is looking at. It's looking to see on your x's, because x's are your domain values, how far left and right do they go. So for in this example here, our domain, we ended at 3 and -3, but I could have used -6. I could have used -306 or positive 306. So I could have went on in either direction forever. So our domain, in this case, is all real numbers. So real numbers, if you recall, are basically all of our numbers together. There are radical numbers, there are rational numbers, there are whole numbers, there are integers, and there are natural numbers. So they can have square roots or cube roots or whatever. They can be fractions, and they can be positive and negative values. What we do, though, is instead of writing domain is all real numbers, we use some math shorthand. So we say D, and we put our two dots, and a parentheses with an X, /X, funny looking E, and a double R, I guess, and then another bracket. So this is read, domain is the set of numbers for X such that X is an element of or belongs to be belongs to, in brackets, real numbers. So the brackets in there are the set of numbers for x. This slashed line right here, that line there is our such that. This funny looking E means element. And our double barred R means that they're real numbers. So the next one says, for any graph you can find the range. So the range is looking at how far up does the graph go and how far down does the graph go. So it's looking at your y values. So in this example, our range was y had to be greater than or equal to 0. Or if we wrote that out in proper form, we'd say that, not range. Oops, I'm getting ahead of myself here. So I put an R for range, and you can use a capital R too, but this is where it's important that you make that distinction between real numbers and range. So the range is set of values for y such that y is greater than or equal to 0. Y is an element of real numbers. So it has one stipulation on there. It can't go smaller than 0, but you can still use real numbers. So I could use roots, I could use fractions, I could use decimals, positives, or negatives. Sorry, I can't use negatives because I can't be less than 0. So a quadratic function is a function that has a second degree polynomial, which just means it has an x squared term, but nothing higher. The graph shape that results is a parabola. So some examples of parabolas. I could have y is equal to x squared minus 7. I could have the function of x is equal to x squared plus 2x minus 5. Or I could have the function of x is equal to x minus 3 squared plus 2. All of those, they're written differently, but they are all still considered to be parabolas or quadratic functions because the highest degree that I have, if I expanded those out, is going to be that squared, or a degree of 2. F of x is just, it's the same as saying y. When you say something is a function of x, you're saying what is the y value. So if I substitute an x into my second equation there, fx is equal to x squared plus 2x minus 5, I'm saying what would be the y value if I substituted in a 2 for my x. Okay, so now we're going to look at some characteristics of our graph, some other characteristics. So if we graph y is equal to x squared using our basic count method, we start at 0, 0, we go over 1, up 1, over 2, up that 2 squared, so 4 over 3, up 9. So I'm going to do my basic graph right there. So I have 0, 0, 1 and 1, over 2, up 4, over 2 to the left, up 4, over 3, up 9, and over 3, up 9. So again, as I'm graphing these, I have to make sure that I do my best to go through the line. And then I also have to make sure that I put arrows on the end, because I've just picked a few values that I'm plotting for, but not all of the values. Okay, I just have to pause here for 1 second. Okay, so now we're going to try the graph for y is equal to x squared plus 4 using the table of values. So what this means then is when I have y is equal to x squared plus 4, I'm going to substitute first in my -3 but I have to add 4 to that. So that's going to give me 9 plus 4 is 13. If I do that for negative 2, I'm going to have negative 2 squared plus 4, so that's going to give me 4 plus 4 is 8. Negative 1 squared plus 4 is going to give me 5. 0 squared plus 4 is going to give me 4. And then I would just continue for the rest. I'll just write in the answers for those. So I had 13, 8, 5, 4, 5, 8, 13. Okay, so let's draw this graph and see what we notice. I'll do this one in purple. So my first point there is at negative 3 and 13. So 1, 2, 3, 13. I've only got 11. So 12, 13 will probably be 11. We'll put it about right there. 8 and negative 2, or sorry, negative 2 and 8 puts me there. Negative 1 and 5. 0 and 4. 1 and 5. 2 and 8. And then 3 and 13. So my graph looks like that. And this graph, my blue graph here, I've kind of curved it back in. My graph should probably be going more out that way than it is curving in, but you still get the idea of it. So what do we notice? Well, basically what we have here is the exact same graph as we did for y is equal to x squared. The only difference is my graph has moved. It has gone up 4 spots. Okay, I'm going to have to repeat what I just said in the last few seconds because I forgot to turn my microphone back on. So that 4 that we put in there into this equation right here, as compared to the y is equal to x squared, has moved our vertex 4 places up. So what did we notice? It's the same parabola. As y is equal to x squared, except, whoops, it has been translated, and those are kind of our technical term for it, just means moved. Four units. So this is because of the plus 4 at the end of the function. Whoops. And function is just a fancy word for an equation. So that is called, oops, not the G, the Q value. So if I take a look at this, my vertex in the purple graph, let's move it down here a little bit. The vertex in the purple graph is now at 0, 4. My axis of symmetry, so that line that's going to cut that graph, so I've got a perfect mirror image, 2 branches are exactly the same, is still that y is equal to 0. Sorry, not y is equal to 0, x is equal to 0. If it was a horizontal line, it would be y is equal to 0. My maximum or minimum, well, I have a minimum because my graph is going upwards. It's a minimum value. So the minimum is at y is equal to 4. My domain for this would be the set of values for x such that x is an element of real numbers. So I can use any x value I want, positive, negative, fraction, root, doesn't matter. My range, though, will depend now on where did my vertex move to. So in this case, my vertex moved up 4, so my range has to be the set of values for y such that y is greater than or equal to 4. Oops, and I should also put in there y is an element of real numbers. Okay, so the third one here, we're going to graph y is equal to x squared minus 3, but we're going to use the count method instead. So instead of doing a table of values, we're going to use the count method. So if I take a look at this graph, my q value is what's being added or subtracted on to my function. So my original function is y is equal to x squared right here. What's being added on is this negative 3. So my q value is at negative 3. So that means my vertex is going to be at 0 and negative 3. So if I do my basic count again, it's going to be over 1, up 1, over 2, up 4, over 3, up 9. So from my vertex, I'm going to do that same count, over 1, up 1, over 2, up 4, over 3, up 9. And again, I do that in both directions, in the left and the right. So I'll do this one in red. So my vertex is now at 0 and negative 3. So 1, 2, 3, that's right there. And now I'm going to do my count. So over 1, up 1, over 1, up 1, over 2, up 4, 1, 2, 3, 4. So remember, you're always going back to your vertex. Over 2 to the left, 1, 2, up 4, 1, 2, 3, 4. And then I go over 3, up 9, so if that was 4, 5, 6, 7, 8, 9. And over 3, up 9. So this graph looks like that. Okay, my vertex for this one, well, I've already identified it here. But I can also look off of there and see that I was correct. It is at 0, negative 3. My axis of symmetry hasn't changed. It's still going right through that x is equal to 0. Maximum or minimum value. My graph is going up, so that means I still have a minimum value. So this is going to be a minimum at y is equal to, how far down did it go? Negative 3. My domain, I can use any x value that I want, so it's all real numbers. My range now has changed, though, because I've moved down my minimum value, so my range is at the set of values for y such that y is greater than or equal to negative 3. Y is an element of real numbers. So in a nutshell, y is equal to x squared plus or minus q. So the q value then translates the parabola up or down. If a q value is positive, parabola transfers up. if a q value is negative, then that shouldn't be transfers, it should be translates. Whoops. So it translates down. The other thing we've noticed is that the y value of the vertex is the q value from the function. So our vertex is going to be at whatever the x is. In this case, our x's were 0 and q. The q value also will tell us what our minimum or maximum value is, depending on whether or not it's a minimum or maximum value, or maximum graph. Okay, so in this section we're going to look at the p-value. So we're going to do a graph of y is equal to x squared using the count method, so just so that it's nice and quick. So y is equal to x squared, my vertex is at 0, 0, over 1 up 1, over 2 up 4, over 3 up 9, and that's as far as I'm going to go on my, whoops, well that's a bad one. So we'll pretend I went through my dot there. There. Okay. So now we're going to try one with y is equal to x minus 4 squared using a table of values. So we're going to see what happens when we use something inside the bracket. So the p-value is being added or subtracted to the x term before we square it. So if I use a 1, I have 1 minus 4 all squared, so that's negative 3 squared is 9. 2 minus 4 squared is negative 2, negative 2 squared is 4. And then we just keep going on and on and on. So this is 9, 4, at 3 it's at 1, 4 is 0, 5 is 1, 6 is 4, and 7 is 9. So if I go to graph this, I'll do this in purple. I'm at 1 and 9. Two and 4. There's 4 right there. 3 and 1. 4 and 0, 5 and 1, 6 and 4, and 7 and 9. So if I connect my dots, what do we notice? We have the exact same graph, it's the same shape. Still doing over 1 up 1, over 2 up 4 if you checked your basic count here. So on this one, I'll just do in yellow and erase it. So I went over 1 up 1, over 1, 2, up 1, 2, 3, 4. Over 3, so 1, 2, 3, up 1, 2, 3, 4, 5, 6, 7, 8, 9. So my basic count is the same. I don't know if that's hard for you to read. It's hard for me to read. So the basic count is the same. I have the same shape of graph then. The only thing is my graph is now moved over 4 places to the right. So it is the same parabola. as y is equal to x squared, except it has been translated. Four units to the right. So this is because of the number in the bracket. So what happens there is, if you take a look, is our p-value, or this number in the bracket, was a negative 4 here, but it's moved it 4 right instead of 4 left. So what we do is we change the sign. So if we change the sign, we have what we call the p-value. So our vertex in our purple graph here, maybe I'll do it in purple. Our vertex is at 4 and 0. Axis of symmetry now, if I wanted to draw the line that's going to cut that exactly in half, it's going to be going right here. So it's going through the middle of the graph. It has to go through the vertex. So my axis of symmetry is at x is equal to 4. My maximum or minimum, it hasn't changed from the original graph. It's still at 0. It's going up, so it's a minimum at y is equal to 0. My domain, set of values for x such that x is any number we want. Our range then, whoops, curly bracket, is a set of values for y such that y is greater than or equal to 0. Y is an element of real numbers. So the p-value mental switch, something to think about and keep in mind every time you're working with the p-value, is before you can call it the p-value, you have to take the number in the equation and switch the sign. So you mentally switch the value of the sign in the brackets. Oops, I'm going to run out of space there. So you mentally switch the sign of the value in the brackets to get the p-value sign. So in that equation, if it had been y is equal to x plus 4 all squared, our p-value would be a negative 4. Okay, so let's try this one. Graph y is equal to x plus 3 all squared using the count method. So let's take a look at what we know here first of all. We have x plus 3 squared. So I have a plus 3 being added inside the bracket so that I know that's my p-value. If I had x squared plus 3 like this, that's a q value. Inside the bracket is p, outside the bracket is a q. So that means my p-value for this would be at, mental switch of the sign, negative 3. So what I also noticed, or what you may have noticed is from my first one, my p-value in this one was a 4. That 4 there also became the value in my vertex. So knowing that then, and because I don't have anything added or subtracted, my vertex is going to be at, sorry, not 4, 0. In this one, it's going to be at negative 3, 0. So now that I have my vertex, I'm going to draw the graph and see what we find out with all the rest. So my vertex is at -3, 0. 1, 2, 3, and 0 is right there. Doing my basic count, over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4, and then over 3, up 9, and over 3, up 9. So if I draw my graph, it looks like that. The line that's going to cut it is going to go through here now. So what do I notice? My axis of symmetry now is going through that -3. -3 was my p-value. So axis of symmetry is at x is equal to -3. Maximum or minimum? Well, my graph is going up, so I have a minimum. The lowest value on there is at, oops, pretend that says at y is equal to 0. Domain, any real number we want to use. The range is anything greater than or equal to 0, and it's also a real number. That last pause, hopefully my interruptions are done. So, taking a look at what we've done here. Our basic equation was y is equal to x squared. Our translated or transformed equation is y is equal to x plus or minus p squared plus or minus q. And usually when we write about it or talk about it in general form, we just say y is equal to x minus p squared plus q. The signs don't really matter when you're saying it generally because you'll put in the proper signs when you write it as an equation. So what we know is this p-value here translates the parabola. Whoops, there should be a p. So p translates the parabola left or right, as we saw in our example up there. You have to remember, though, to do the mental switch. Of the sign. Whoops, sign. Q then translates our graph up or down. And there is no switch assigned for Q. A couple of notes about our vertex. So what we've noticed after drawing a couple of graphs here is that our p-value is the x-coordinate of the vertex. And whenever I talk about p-value, that means that I have changed that sign. Without the sign change, it's not technically the p-value. And our y-coordinate is the q value. Okay, so let's try putting this all together. So you can either follow me through as I'm doing this, or you can pause and try it on your own and then check it to see if you got the right answer. So the graph that we're going to try is y is equal to x plus 2 squared minus 5. So we want to use the count method for this. We're not bothering with table of values. Table of values, unless the question specifically says, don't do because it takes way too long. So what you always want to do when you're graphing is you want to identify what are your values. Right now we're only looking at P and Q. Later on we're going to have an A value that we look at. So based on this, my p-value, and it can't be called my p-value until I do that switch of the letter, so the p-value is what's inside, so it's a -2. My q-value then is what is being added or subtracted to the squared part, so it's a -5. So this means I'm going to go 2 left. This means I'm going to go 5 down. So 2 units to the left and 5 units from the down. They're 5 units down. Remember, my base graph would be y is equal to x squared. So my vertex for that would be at 0, 0. My vertex for this one now is going to be at that p and q value. So my vertex is going to be at -2, -5. So my vertex was -2, -5 right here. So from my vertex, I'm going to do my basic count. So remember, the basic count is going to be over 1, up 1, over 2, up 2 squared, so 4, over 3, up 3 squared, so 9, over 4, up 4 squared, so 16. You can put little dots in there so you know. Okay, so let's try graphing that and see what happens. Over 1, up 1, over 1, up 1. Remember, you're always going back to your vertex. Over 2, up 4, and over 2, up 4. So it puts me at -1 on the y. Excuse me. Over 3, up 9. That was 4, 5, 6, 7, 8, 9. So I'm at 4. And then over 3, up 9 on the other side. It's going to be there. And then over 4, up 16. So that should put me at 9, right? 9, 10, 11, 12, 13, 14, 15. Oh no. Oh, too bad I can't add. I'm going 7 up. So it should put me at 11. 9, 10, 11, 12, 13, 14, 15, yeah, 16. And 16 over there. So this is what my connected dotted graph would look like. So my axis of symmetry for this, it has moved. It's no longer at 0, it's now going through -2. Whoops, that's supposed to change color and it didn't. So there's my axis of symmetry. My axis of symmetry is at x is equal to -2, which also happens to be my vertex. So your axis of symmetry is also your p-value. So your axis of symmetry is always going to be at x is equal to your p-value. So in this case, x is equal to -2. Maximum or minimum? Well, my graph is going up, so that means I have a minimum value. And like I said before, my minimum is affected by my q value, which is the y-coordinate of the graph, so that means that it's going to be here at -5. So it's going to be everything greater than -5 is where that minimum value occurs, or it occurs at y is equal to -5. Domain, set of values for x such that x is an element of real numbers, and my range, set of values for y such that y is greater than or equal to -5, and y is also a real number. Okay, so that is it for our introduction part to graphing equations, the vertex, using the vertex graphing form. At the front page there, your assignment was a worksheet 3.1a, which you can pick up for me, and then textbook questions number 2, 3a, 7b, 8a, and 10a. So follow the instructions in the question. If it tells you to do a table of values, do a table of values. If it just says to graph it, then use the count method whenever you can, so you get really good at that. I have lots of graph paper here at school, so if you want to grab some of that, then feel free to help yourself.